Okay, this lesson is about graph interpretation. In particular, it's about force versus time graphs. But in order to understand how to interpret a specific graph, let's look at some general trends for any graph. Now, for any graph, no matter what the axes are, you always want to look at the slope and you always want to look at area. You want to ask yourself if those things have any physical meaning. In this case, we've got a force for the y-axis and we've got time for the x-axis. So if you ask yourself, does force divided by time mean anything? And does force times time mean anything? Well, let's take a look at what we know about force and time. We know that force is related to time because time is in this acceleration term. It's change of velocity divided by time. So what about this times time? You would have m times delta v over t times t. Well, those two t's would go away, and you would get the product of force times time equals mass times change of velocity. Mass times velocity is momentum, so sounds like you have impulse. The definition of impulse is the change of momentum, and now we've shown that that can be the product of force times t. But hey, wait a second, weren't we looking at this graph and wondering, hey, what is the product of f times t? Does that mean anything? Sure. That means the change of momentum, or the impulse. So now when you look at a force versus time graph, you know that the area underneath the curve is going to represent the impulse applied to an object. Alright, now we can do some sample problems. Example 1, a 5 kilogram object with initial velocity of negative 3 meters per second undergoes the forces in this graph. And what is the final velocity afterwards? Okay, this graph looks like we have a combination of two triangles. Here's the first one in blue. Looks like we've got a base of 5 and a height of 5 as well. So the area of a triangle, 1/2 base times height, should yield 1/2. 5 times 5 is 12.5. And the other triangle, we're going to shade with a different color. Looks like the base is 2 and the height is 10, so 1/2 2 times 10 is 10. So the total area is 12.5 plus 10. Alright, so we'll put change of momentum is 22.5 kilogram meter per second into our list of information. And then we'll start looking for final velocity. Well, it's a good thing we have this big old impulse equation here with all these terms, and we can find these terms right here, as well as change of momentum right there. So here's a nice way to use this equation. You can just grab whatever you need. Sorry about all that tapping noise. That's the only downfall to recording this way. Alright, so we've got the change of momentum, which is like the area, and we just found out that was 22.5. And we want to solve for final velocity. Well, this term right here, change of velocity, is like v final minus v initial. So keep that in mind. We're going to substitute that in. And we'll bring everything down. V final is the thing we're solving for. So let's see what happens. We've got 22.5 is equal to 5 times Vf minus negative 3. So let me make some room here. The rest is really just algebra. You would divide both sides by 5, and then you would subtract 3 to get the Vf. So what do we got? We've got 4.5 minus 3, so final velocity should be 1.5 meters per second. Hopefully that was Easy enough. Let's do another one. Okay, next example. Identify the change of momentum and the final velocity of a 5 kilogram mass that undergoes the following forces with an initial velocity of 2 meters per second. So kind of the same process. The area should be just the area of this triangle. Looks like we have a base of 10 and a height of 5. So 1/2 base times height should give you an area of 25. That means we have a change of momentum of 25 kilogram meters per second. How are we going to get final velocity from that? Well, they gave us initial velocity was -2 meter per second. They gave us the mass was 5 kilograms. And now we know the change of momentum from solving for the area. We know that is equal to 25. So just like before, we can consult this formula up here. We were given the change of momentum. We know that has to equal to mass times change of velocity. So let's use that. I'll bring down the VF minus VI from before. Very similar question and very similar process here. Alright, so the area was 25, the mass was 5, and the initial velocity was -2. And we want to get VF by itself. First, let's divide by 5 and get rid of that 5. So you've got 5 is equal to VF plus 2. So final velocity has to be 3 meters per second after you subtract 2 from both sides. Alright, last one. Oh man, looks like we've got a whopper here. Just kidding, it's kind of the same stuff. Alright, it looks like I would split that up into a rectangle right here, this shaded region, and then a second shape that's a triangle right here. So maybe pause the video, see what you get when you try it yourself, and then press play and see if we agree. Okay, for that first rectangle shape, I get an area of 20. And for this triangle shape, I get an area of 12.5, which means our change of momentum is 32.5 kg meters per second. And they would like to know the final velocity, so let's solve for that also. Delta P equals VF minus VI was it no, it's 1 kilogram. Oh, that's easy. 1 kilogram and VI was 0. Okay, then we don't have to do much thinking there, because then it's just VF equals 32.5. And that's it. That's how we do these. I hope that makes sense. And honestly, if you're going to remember anything from this video, don't remember that specifically force versus time graphs have an area equal to impulse. I would just say in general, remember this, because you have no idea what the next graph you're going to have to read is. But you want to always ask yourself, does it mean anything if you multiply the axes or if you divide the axes? And what does that mean?